So, if we're talking about an exponential function, and I'm going to make one small requirement. I'm going to force b to be greater than 1. It doesn't have to be. It could be between 0 and 1, like 1/2, 2/3, something like that. It just gets weird when things like that happen. So if we restrict b to be bigger than 1, then we get a general picture. And the general picture looks something like this. If you graph an exponential function, it treats the x-axis as a horizontal asymptote in the negative direction. It's not a horizontal asymptote in the positive direction. But if you go off to the negative infinity, the graph gets closer and closer to the x-axis, but it never ever touches it, which is kind of cool. And then after it passes this point, which has a coordinate, by the way, of 0, 1, it grows what's called exponentially. So if you hear the things about exponential growth, this is what we're talking about. Of course, what's the domain of this graph? Remember domains? So if this is your picture, the domain would be?
Negative infinity.
Negative infinity to? Positive infinity. All right, the trickier one, range. I don't know why it's trickier, but for some reason...
Negative infinity.
Nope. Remember I said it gets closer and closer to the x-axis, but it never touches it, and it definitely doesn't go below it. And we're talking about y values here, which are up and down. So how far down does this graph go? 0. That's as low as it's going to get, but does it ever touch 0? No. So we get a parentheses 0, and it goes off to? Positive infinity, because it's growing straight up. So the domain of the exponential graph is all real numbers. The range is only positive numbers. Only positive numbers can be used as the range. We also talked about logarithmic functions. Well, we haven't talked about it as a function per se yet, but this would be a logarithmic function. Again, we're going to force b to be greater than 1 to make things nice. And we already know that this g of x is really the inverse of the exponential function. So do you remember how to graph an inverse function? What happens when you take a regular graph and an inverse graph? What happens to all the coordinates? They just switch around. So here we're positive on the y-axis and really low on the y-axis and negative very far out on the x-axis. That's going to correspond to really negative on the y-axis and a little bit positive on the x direction. So this graph is going to crawl up the y-axis. It's going to hit this point, which over here was 0, 1. So over here it's going to be 1, 0, and then it kind of grows like that. So they look really similar, except one crawls along the x-axis, the other one crawls along the y-axis. And they both go through that corresponding point. Over there 0, 1, over here 1, 0. Instead of growing exponentially up, remember it reflects over that line y equals x, it's going to kind of grow really slowly. So when we talk about logarithms, they have a very slow growth, where exponentials have a very big growth. One application for logarithms is the Richter scale. Anybody know what the Richter scale is? It's earthquakes. You know, if you have a magnitude 7 earthquake, it's a Richter scale. And what they do is they change the number to be smaller than what it is. It's supposed to be the energy released from a earthquake. Imagine how much energy is released in an earthquake. That could basically level a city. It's a lot of energy, so the number's really huge. They use logarithms to bring it down into a smaller number that we can, evaluate different earthquakes. Magnitude 6, magnitude 7, and so forth and so on. All right, what's the domain of this function?
Negative infinity.
Now, do you remember anything else about inverses? The domain and range of inverses, all they do is switch. So the domain here is going to be the range over here. It starts at 0 and it goes off to infinity. And the range of the logarithm is going to be the domain of the exponential.
The range can't be negative.
Huh?
No. It's the inverse, so it can be.
It's an inverse, so you take the domain and range, and all you have to do is flip them. So the range on the exponential becomes the domain of the logarithm, and the domain of the exponential becomes the range. And if you look at it, it actually corresponds. The range here goes down to negative infinity, then this arrow is going off to positive infinity. And the domain, it starts at the y-axis and moves to the right. So it starts at 0 and goes to the right. The one that's really important is this one. This one tells you cannot take the log of a negative number. So this is illegal. Log base 5 of negative 3 does not exist because it is not in the domain of that function. So you cannot take the log of a negative number. So if any chance you type in log of a negative number, your calculator is going to say domain error. And it's not that you did anything wrong, it's just you cannot take the log of a negative number. And you might fall into that trap, and there's ways of avoiding it sometimes.
It equals what?
Hmm?
You said it equals what? None.
Does not exist.
Oh, okay.
It's a neat little abbreviation. Or you can put this. That works fine. All right. So last class we talked about just basic logs with a different base all the time. I want to talk about two special ones. The common log and the natural log. Now, on your calculators, there's two buttons. One of them is LOG. That's the common log. We'll talk about that in a second. The other one is LN, and that is called the natural log. So the common log is defined this way. It's the log base 10 of x. But instead of writing, that base 10, we consider it understood. Kind of like x to the first power, you just write x by itself. So on your calculator, that is just written log of x. So if I ask you what is the base of log, without saying what the base is, you have to tell me it's 10 automatically. Same thing with the natural log. The natural log is base e. Instead of writing log base e of x, there's an abbreviation called ln. So if you see ln, the automatic base is e, that fancy number, the natural number. Therefore, that's why this is called the natural log. So these are two logarithms you have to get used to. So for instance, for example, if I give you log of x is equal to 3, can you solve for x? What would you do?
So can we replace that log?
The way you're going to do it is, you can't solve it as a logarithm. So there's a way of changing it into, it was the end of last class, changing logarithms into exponentials. You start off with, what is the base? The base is 10. Then what is the power? 3. What's it equal to? X. So we get x is equal to 1,000. It allows you to solve equations. It's a neat little trick. Alright, how about this one? Log ln of x minus 2 is equal to 1. If you want to solve this nice simple equation, what's the base?
E.
And it always starts off with asking that. What is the base? In this case, it's e. What's the exponent? 1. What's it equal to?
X minus 2.
X minus 2. How do you solve for x?
Okay.
How do you solve for x?
Did you add?
You add 2. So you get x is equal to e plus 2.
How do you know about the E?
You don't care. It's just a number in your calculator, just like pi. Seriously, it's just like a symbol. You just write it down. You can treat it like a variable if you want to, but the calculator knows it's equal to 2.7128, blah, 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 blah. It's just a number. But if you want, you can treat it as a variable and it still becomes the right answer. That you're solving for. How about a tricky one? ln of the log of x is equal to 1. Now this is a composition of functions, the composition of the logarithm inside of the natural logarithm.
So
All right, what base can we get to first?
The parentheses log of x.
The one on the inside, we can get to the base inside. No, you can only get to the base on the
So
outside.
E.
So you get e from here, raised to what power? 1, which is from the other side, must be equal to log of x. Okay. What base can I get to now?
Log of x.
What's the base?
10.
10. So you take this and you write 10 raised to what power?
1.
E. The other side. You always go to the other side to get the power. So the base comes from here, the power comes from the other side. And it has to equal x. So we just solved the equation. X has to equal e to, or 10 to the e power. Isn't that crazy?
Yes, very crazy.
But when you're working with a composition of functions in this, you have to start on the outside and work your way in. And you're always concentrating on what's the base of the outside one. In this case, it was e. Let's go and reverse the order of this thing.
And there's no way you can just put that on the calculator.
Good God, no. Because it's an
That's a
equation.
good question.
It's an equation. You can't type in equations. At least into your calculators. What if I change the order? Log ln of x is equal to, yeah, let's keep it as 1. It makes life easy. Alright. What do I take first? Well,
The outside.
the base on the outside is
10.
10. The power that it's going to get raised to is
Uh,
1. And it's going to equal ln of x. Alright, now where do I go? ln of x has a base of
E.
e. You're going to raise it to
10.
the 10th power, and it's going to equal x. And there you are.
Okay, what about that one?
10 to the first is 10. If it
I
was
mean,
10,
10, yeah.
if it was 2, I was going to make it 2, but then it was like 10 to the second would be 100. And then you'd have e to the 100th power, which I hope to God your calculator cannot calculate, because that's a huge number. Alright, so that's the natural log and the common log, and some of its uses. I mean, I could ask you something like this, you know. Log of 1,000 is equal to,
Log of 1,000.
15.
There's 10. Oh, well, you saying equal to?
the base is 10, but log base 10 of 1,000, what power do you raise 10 to?
10 to the
get?
third.
10 to the third, so the answer would be 3. Or you could have ln of e to the negative 3, and the answer would be?
Fraction.
The base is e. What power do you raise e to get to e to the negative third?
LN. Oh, wait.
Easy answer. Think easy.
Is it one?
Negative 3.
Oh,
Negative 3. The power you have to raise e to get to e to the negative 3 is negative 3. Up here, I could have wrote this as log of 10 to the third is equal to. What power do you raise 10 to get 10 to the third? 30.
What?
Ah, it's one of those laws we went over. Log base b of b to the, well, actually we probably didn't. R is equal to what?
Oh, yeah, we did.
R. I thought we did this one. Log base b of b to the r is equal to r. They're inverse functions, so they go poof, and the r's kind of popped out. It's one way of looking at it. Alright, so the rest of the junk. We have to talk about laws of logarithms. There's only 3 you have to know. Whoops, wrong one. Ah, it's only the last couple questions for this junk. These are the easiest things on the entire exam. Dealing with logarithms and exponentials, there's not much to know.
Talking about the overall exam.
Oh, the overall exam, yeah, it's going to be a killer. But it's only got 33 questions.
You said 25. What are you talking about?
Yeah. But how are we going to have time, an hour to do all those questions? We don't even
we're going
have
to stay
time.
longer. We can stay longer. We can come in earlier, too.
Oh,
I could be here at 8 o'clock.
Okay.
Especially for some people that have classes right after this.
I won't even think about
So they have a class in here on Monday?
After this one, yeah. I don't think there's one before us.
We gotta go to the library again.
I don't like going to the library. It's distracting.
Ah, laws of
Give us
laws.
a take home by.
That sounds good.
Yes.
Laws of logs.
Can you do that?
What?
Take home?
No.
You don't trust this?
No.
That's
Trust is a interesting. I definitely don't trust you. You're already texting over there. Let's start off a little weird. Given that b to the x is equal to this capital M, and b to the y is equal to capital N. You're not going to know where I'm going until I get there, so don't worry about it. I'm just setting it up right now.
B to the fourth. I mean, why?
To the y. B to the y equals N. Now, after I write these down, you should be able to tell me two more relationships between bm with the x and bn with the y. How do I change this one into a logarithm? What would it look like? Well, I can start it off log
B.
base b. You gotta get that word base in there. Base b of m is equal to x. And this one over here, if we convert it into a logarithmic form,
Log base B.
log base b of n is equal to y. So it gives me four relationships that I can use in a proof that I'm going to do. So here's what I want to prove, or what I want to work with. I want to look at a log that has a base of a product. Now if you remember, the answer to logarithms are exponents. So you would expect this thing to behave like the laws of exponents. So when you multiply two things together, what happens to their exponents?
Yeah.
You add them. So I'm expecting a plus sign someplace in this proof. So the first step is I'm going to replace m and n with what I have up here. M is going to get replaced with b of x, b raised to the x power, and n is going to get replaced with b to the y. And that's why I chose them, so I can do these nice little substitutions. Now, after I do that substitution, what can I do with b to the x times b to the y?
And multiply.
Multiply the bases together by taking their exponents and adding them. So this becomes log base b of b raised to the x plus y. Perfectly legal by the laws of exponents. Okay? But now we have a neat little thing going on here. This is log base b of b raised to the x plus y. Go back over to the law I wrote over here, which was log base b of b to the r is equal to r. What does this one equal?
X plus Y.
Just x plus y. The log and the base b disappear, and you're left with x plus y. But what's x equal to?
10.
Come back up here. Oh, look, x all by itself. What's x equal to?
Log B of M.
Log base b of m. What's y equal to? Log base b of n. So this becomes log base b of m plus log base b of n. And I'll bring down the other side. The log base b of the product, mn, is equal to the log of the first one plus the log of the second one. Very nice law.
It sounds like you speaking.
You want numbers? I'll give you numbers.
Was that an equation or that's a way to use?
That's a formula.
Oh, okay.
That is a way of separating a product, the log of a product, into the sum of the logs.
No, I mean that you just showed us all that to get to that formula.
Oh yeah, don't I always do that?
that?
I always do that.
I'm not even surprised anymore.
Look, I showed you how to find slope and y-intercepts and all that fun stuff, and I always showed you why it works. I don't sit there and go, here's a formula.
You see, I'm just looking, right?
Here's a formula.
The hell,
I don't do
you
that.
Gotta do all that.
This is what you're going to do with that
I
formula.
was like, wow, they didn't have all these numbers. They gonna throw something.
She always knew it'd be a formula too. Nobody else would like.
So this is the uses of it. If I have log base 2 of 8 times x plus 3, I can simplify this or expand it out to simplify it in the following fashion. Since this is a product, I can say log base 2 of the first one plus, the product turns into a plus, and then you just tag on log base 2 of the second one.
And then you can put it in your calculator.
No calculator. You can't type anything. It's log base 2. The calculator only works in log base 10 or E. But what is log base 2 of 8 equal to? What power do we raise 2 to get to 8? 3. So this simplifies to be 3 plus log base 2 of x plus 3. This is called an expansion. We're expanding. So, expand. We can expand. Yeah. We can also contract. We can take something that looks like log of 5 plus log of x minus 3 plus log of y. Now, what's the base of that one? It's log base 10, but I'm not writing the 10. All I have to do is write that little g. Look at him. He is on his cell phone. He is so sad. Just, disrespectful beyond degree. You're depressed. So what I can do here, since these are all pluses, when I bring them all together, they're going to convert into times. So when I see plus, I'm going to make it multiplication on the inside. How many times am I going to write the logarithm? Once. Instead of having multiple logarithms, I'm going to condense it down to one. So the first thing I recognize is, well, it's all multiplication. You're going to write the log exactly once, and then write down what's inside. Well, it's going to be 5 times x minus 3 times y. And you're done. So you can either pull these things apart or you can push them all together. When you pull them apart, you're going to get multiple logs. When you push them together, you're going to get a single log. That's all there is to it. Not that bad, right? All right, second law I'm just going to give to you. It works exactly the same as that over there, but it is going to be m over n. Then you get b to the x over b to the y. What happens to your x, y then? They're going to subtract. So the next law is the log base b of m divided by n is equal to log base b of m minus log base b of n. So I'll give you a hint. Now we're going to be dealing with fractions. And the hint is this. If your logs are positive to begin with, those answers go in the top. If your log is negative, those answers go in the bottom. They're like negative exponents. They're on the wrong side, and you have to kind of shift them down. So, for example, simple one. Log base 2 of 16 x plus 2 over y minus 3. And I want to expand this. I want to expand this. Whatever is in the top gets a plus. Whatever is in the bottom gets a minus. So it becomes log base 2 of break it apart into pieces. What's the first piece? 16. So it's log base 2 of 16. It gets a plus because it's in the top. I mean, there's a plus out front here if you want to write it. What's the other piece? Well, how do I write it though?
Wow.
Before the log. Plus log base 2 of x plus 2. You can't separate pluses. You can only separate multiplication and division. All right, what's the next piece?
Y minus 3.
All right, so it'll be log base 2 of y minus 3. What goes in front? Minus, because it's in the bottom. And then the only thing is, what's log base 2 of 16 equal to?
8.
Okay. What power do you raise 2 to get to 16? 4. So that's how it breaks down. It's not that hard. Top pieces get a log and they're positive. Bottom pieces get a log and they're negative.
It's the easiest thing you done gave me all this.
See, I tell you, this stuff is nice. What if I want to contract?
You gotta finish the rest of the problem, don't you?
Well, 4, this, that's all.
Yeah.
You expanded it. 4 plus log base 2 of x plus 2 minus log base 2 of y minus 3.
Okay.
That's it. You can't do anything else to it. What if I have log of x minus log of y plus log of z plus 1 minus log of x minus 1. It looks horrible, but it's really not. How many times am I going to write the log if I'm going to contract this?
One.
I'm going to write it exactly once. The people that make mistakes write more than one log. Once you get used to the habit of just writing a log, there's pluses and minuses, so you might as well write a fraction bar. What goes in the top?
Positive.
Which one?
One.
I'm not going to write log again. I only write it once. X. What else goes up there? Y definitely does not go up there because it has a negative in front of it. So it's the only other thing that has a positive in front of it.
Z.
Z plus 1. So I'm going to write Z plus 1. What goes in the bottom?
Y.
The Y. What else goes in the bottom?
X minus 1.
And they're all multiplied together. And this is your final answer. Positive pieces go in the top, negative pieces go in the bottom.
See, it's easy with you.
That's how that last.
I can just say, yeah.
Anytime I have ever taught this, people don't mess it up horribly. You know, little things they'll mess up, like sometimes signs and whatnot. But other than that, they don't usually screw this stuff up. Yeah, but people with sign mistakes will always mess up something. The last law deals with this, and it's actually the most powerful law. Log base b of m to the k power. Now, if k is a whole number, like 4 or 5 or 6 or something like that, let's just do a little sub looking at things. If I have log base b of x to the third power, I can rewrite this as log base b of x times x times x. Agreed? Because, you know, x to the third power is just 3 factors of x. Now, if I use the first law, which means products turn into sums, we're going to get log base b of x plus log base b of x plus log base b of x.
See, now I don't even know what you're doing anymore.
I'm just starting here with log base b of x cubed, just to see what happens. X cubed becomes x times x times x. Now I can use that first law that says I can change products into sums. I can change the log of a product into the individual log of their sums, log of each factor. But here's the cool thing. It started off as 3 factors of x, but now we have 3 sums of log base b of x. How do you add multiple numbers together? Like if I asked you to add 7 5s together, do you know the answer? You would multiply them. You would go 7 times 5. So here, what would I multiply?
Log times 3.
Log base b of x times
3.
3. So this becomes 3 times log base b of x. So what happened to the 3? Where did this 3 come from?
It's 3 of them.
It came from the cube. So what happened to the power? Well, the power actually ended up in front. So it started off as an exponent, but it ended up as a regular old number, which is kind of cool. And that's extremely powerful to change exponents into regular numbers. So the law is this. Log base b of something raised to a power is the power times log base b of the base. Ooh, that's supposed to be an m. M. So this is actually the best law of logarithms. Absolute top one to use.
That's the one I understand.
That's the one you understand the most?
So you're talking about like one problem with each one of these rules?
All I'll have is one expansion, one contraction. So now we can do a more complex expansion. Log base 3 of the square root of x minus 1 times y to the third power over z plus 1 raised to the 4/3 power. It looks horrible, but it's really not. Very, very simplistic. You just have to remember, top things get pluses, bottom things get minuses, and powers go out front. So all you do is kind of figure out what the power is and then just throw it out front. Do it piece by piece though. So you're going to do log base 3 is the first thing you write. Of what?
What are we? What?
Pieces. Just take pieces. What's the first piece?
Y.
No, it is not the y.
Oh, well, X minus X.
It's the square root of x minus 1. You can't pull it out of there. You have to take the whole piece. So this becomes the square root of
I was looking at it.
x minus 1. All right. Next to it is that y cubed. Is it positive or negative?
Positive.
So it'll be plus.
Y cubed.
Nope.
I thought so put the thing out in the front.
We'll get to it. We're going to do it step by step. We're not going to try to do it all at once. That makes mistakes. So you take log of the first piece, log of the,
Second piece.
so don't forget log base 3 of y cubed. And it's positive because it's in the top. What comes next? Before the log. Is it plus?
Minus.
It's minus. Why is it minus? It's in the bottom. And then it goes log base 3 of
Z
Plus 1.
z plus 1
fourth of
raised to the 4/3 power. Once you separate it with addition and subtraction, you get rid of any parentheses that might be lying around. No, you cannot touch these because they're pluses and minuses. They're grouped together. Now you can pull powers out front. What's the power of a square root?
2
No, that's a square. What's the power of a square root?
1
A half. That's a half. So we're going to pull a half out front. Log base 3 of x minus 1. You have to put the x minus 1 in parentheses. Otherwise, it would be log of x minus 1. All right, what goes out front here? The 3. So you get 3 log base 3 of y minus
minus 4/3
4/3 log base 3 of,
Z
and make sure it stays in parentheses. And you're done. That's it. Now, contract. I always found contractions to be easier. Some people like expanding better, but I've always liked contractions.
Stuff and labor.
Sometimes they get a little tricky. Like if you have 2 log of x minus 1 minus 1/3 log of y minus 3 minus 4 log of z. Alright, since we're going to contract these, how many times am I going to write the word log?
What?
Once. Now we're going to do this in one fell swoop. So log, parentheses, and we're going to have a fraction, because some of them are positive and some of them are negative. What goes up top?
All the X positives. minus
X minus 1.
and
Don't stop there.
X minus 1 squared.
That 2 is going to come up, so it's going to be x minus 1 squared. Alright? What else is up top?
That's it.
That's it. What's in the bottom?
Y minus 3 to the third.
To the third power. What third power? What radical is that? What's a third power as a radical?
Cube root.
Cube root. So you either write it as y minus 3 raised to the 1/3 power, which is fine. Personally, I like writing the cube root of y minus 3. But either way is perfectly fine. If you write parentheses, raised to the 1/3 power, I could care less. All right, what about the z here?
Minus 4.
Minus 4? You don't put minuses in here. This is all multiplication or division. So times, give you a hint, z to the 4th power. And you're done. What time is it? We got a minute or 2. So, why are these important? Well, let's say you're looking for $5,000. You're starting off with $1,500. You're going to put it into a bank account that earns 5% interest, compounded monthly, and you're going to do it for a certain period of time. The problem here is I need to solve for
T.
t. And t is an exponent, and I've never showed you how to solve for t to begin with. What would you do first?
Divide the exponent.
No.
1500.
You cannot distribute the 1500 because there's a power up there, and multiplication does not come before exponents.
So you gotta do the exponent first.
Yeah.
No, I can't do the exponent because it's a variable. The only thing I can touch right now is
5,000.
I can't touch 5,000. It's on the other side of the equation.
15.
1500. What can I do with the 1500?
Divided.
Yay! So divide 1500 from both sides. It's the only loose
That's what you
piece.
said.
I didn't say it there.
Who did?
Me too.
Oh, I didn't hear you. So divide both sides by 1500. What's 5,000 divided by 1500? Calculators come in handy. What is it?
3.3.
3.3 exactly, or 3.33333?
3.333.
So 3.33 I'll put down. Equals. What about this 1 plus 0.05 divided by 12? That's just a number, isn't it? So we can do a little calculation. What's 1 plus 0.05 divided by 12? It's going to be 1.004.
004.
004? 004. This number is being raised to the 12t power. Okay, now I'm trying to solve for t, but t is high, and I can't deal with t high. So what's the only thing that's going to bring t down?
Do the reciprocal.
What's the only thing that's going to bring the t down?
The log.
A log. So what we're going to do is we're going to log both sides of the equation so we can bring that power down out front. So we're going to log this side, a common log, and log this side, same thing, a common log. Log base 10 on your calculator. So the left-hand side is staying log of 3.33. The right-hand side, what happens?
The 12t
Goes up front. So you get 12t times log of 1.004. Now everything is in a linear fashion. It's all on one line. Nothing's up high, nothing's down low, and we're pretty happy. How do you solve for t? Which is right there. What do I need to get rid of?
The 12.
The 12
You divide it.
and the log of 1.004. So you're going to divide both sides by
12 log.
12 log of 1.004.
I missed that step.
What?
I was writing.
We're trying to solve for t. What's next to the t?
Okay.
The 12 and the log. To get rid of them, since it's all multiplication, I'm going to divide. So divide this side by 12 log of 1.004. Now when you type this in your calculator, be really, really careful. You need a parentheses at the beginning of 12 and after the 1.004. Because there's two pieces in the bottom. Your calculator will go log divided by 12, get an answer, then multiply it by this. I need to divide it by this whole thing. So when you type it in your calculator, you type log 3.33, end your parentheses, divide, start with the parentheses, and then type the rest of it. I have no idea what the answer is, since someone has my calculator. I wonder who.
I got 25.
25?
1.
Hang on. 25? 1, 1. So 25 is what t is equal to. 25, what do you think that represents? T is time. Time is measured in for banks, years. So this would be 25 years to convert $1,500 into $5,000, earning 5% interest.